Welcome to the Explainer. Today, we're going to break down a really simple trick that physicists use to literally see the invisible forces that are all around us, from the pull of gravity to the friction that keeps us from slipping.
Okay, so let's jump right in with something that feels, well, kind of like a physics magic trick. Picture this. You stand on a regular bathroom scale, right? You get a number. But what if you take that exact same scale, put it on a steep ramp, and stand on it again? The number actually goes down. So, did you magically lose weight? What's going on here?
No, this isn't some crazy new weight loss hack, I promise. It's just physics doing its thing. And the key to unlocking this whole mystery, well, it all comes down to a surprisingly simple drawing.
Right, so to get to the bottom of this, we need a special tool that physicists use all the time. It's what helps them visualize all the pushes and pulls acting on an object.
And that tool is called a free body diagram. It sounds a little technical, but the idea is super simple. You basically free an object from everything around it and just draw the forces acting directly on it. That's it.
I love this way of thinking about it. Welcome to Force Accounting 101. It's perfect, right? You're basically doing a full accounting of all the forces to figure out, okay, where is this thing actually going to go?
And you know what the best part is? There's a super simple 4-step recipe for drawing one of these things, and it works every single time. Let's break it down.
Okay, so step 1, you isolate your object. Just focus on the one thing you care about. Step 2, identify all the forces. What's pushing it, what's pulling it. Step 3 is easy. Just draw a dot to represent the object. And finally, step 4, you draw and label an arrow for each force coming out from that dot. Easy, right? All right, before we can draw these diagrams, we've got to meet the main characters, the most common forces that show up all the time. So here's our main cast of characters. You got gravity, that's your weight, and it always pulls straight down. Then there's the normal force. That's the push you get from any surface, and it's always perpendicular to that surface. You've also got friction, which always tries to stop motion, and tension, which is the pull you get from a rope or a cable. And of course, an applied force is just, well, any other push or pull. Okay, enough talk. Let's actually put this recipe to work and see these diagrams in action with a couple of real-world examples. All right, first up, a book just sitting on a table, totally still. What forces do you think are at play here? Well, you've got gravity, of course, pulling the book down, but the table's not going to let it fall, right? So it pushes back up with an equal and opposite normal force. Because those two forces are perfectly balanced, they cancel each other out. The net force is 0, and the book doesn't move. Simple as that. Okay, scenario 2. Now, what happens if we push that same book, but we push it so it slides across the table at a perfectly steady, constant speed? Now, this is where it gets really interesting, and it trips a lot of people up. Even though the book is moving, the forces are still perfectly balanced. Our push to the right is being matched exactly by the force of friction pushing to the left. Since they cancel out, the net force is still 0. And 0 net force means 0 acceleration, which is why its velocity doesn't change.
But what happens if we stop being so gentle? What if we push harder so the book actually speeds up?
Haha! Now the forces are unbalanced. Our push is now greater than the force of friction fighting against us. You can see our applied arrow is longer. This creates a net force to the right. And that is what causes the book to accelerate. It's literally Newton's second law in action right there on the table. Okay, so we've had our training montage, we know the rules, we've seen some examples. Let's go back and solve that mystery from the very beginning. So, back to you on that tilted scale. Here's the most important rule to remember. The force of gravity, your actual weight, it always points straight down. Doesn't matter what angle you're at, it's always pulling you toward the center of the earth. But here's the big secret, the twist in the story. A scale doesn't actually measure gravity directly. Nope, it measures the normal force. It measures how hard it has to push back up on you. And when you're on an incline, that push, it's no longer pointing straight up. It's pointing perpendicular to the ramp.
And because that normal force is now at an angle, it's only supporting a part of your total weight, just a component of it. The rest of that gravitational force is actually trying to pull you down the ramp, so the scale only reads the part of the force that's pushing directly down into it, which is less than your full weight. That's why the number is lower.
So, you see? It's not magic at all. It's just a matter of seeing the forces clearly. And that really leaves us with a final thought, doesn't it? If this simple little drawing can reveal why you seem to weigh less on a ramp, what other invisible forces shaping our world could it help us see?